Part 3. Now it's time for Yang. Starting from the beginning, what is the purpose of Yang? It's very important to understand why we need Yang before going into how Yang modules actually look like. And as I presented previously, it's a data modeling language, a domain-specific language, if you so like, for specifying the relevant data that can be manipulated as represented externally by the box. So it represents a black box presentation of the device, which data can be read, which data can be configured. And it goes hand in hand with the NETCONF protocol. It specifies a tree structure. So anything you define in Yang or the Yangs that you receive represents a tree structure. This was a explicit choice by the NetBot working group, because if you look at configuration data for the devices, they are hierarchical in structure. They are not object-oriented in their nature. It's a hierarchy of definitions. So it defines a tree structure of the data that can be manipulated and their types. And as we've said several times during this tutorial, it makes an explicit distinction between configuration data or not. So going back to the very simple and stupid Acme box I've been using in this example, there is a tree structure. We have two containers on the top, one which I call properties, one which I call interfaces. Within the properties, we had a couple of things that could be configured. For example, the name of the box. So here's one configurable item called name, is of type string. So the tree structure is properties slash name, type string, can be configured. There's another structure called interfaces slash interface. In this case, we have a number of interfaces. It's a list, and every element in the list is indexed by its name. So every interface has a name. So there is no problem in having several things with same name, because they're different part in the tree. So every interface has a name. It's a type string, and it's configuration data. So this means that the management system can create interfaces and give them a name, as we have seen in the previous demo. Imagine you have an operational state of the interface as well. So the upper state of an interface could be up or down, for example. That would make it into enumerated, and that is not config. This is something that the management system can read, but the actual value is in control by the system itself. So doing a get config of a device would not include the upper state. So remember the tree structure. The tree structure represents how to reach a specific element. Every element could be config, not config, and it has a defined type. So continuing with the same example, here is corresponding Yang data model. You put Yang into modules, and remember, as I presented initially, don't confuse modules with the complete device. You should define small modules and making the device support a set of modules corresponding to its functionality. You give a module a name, and here we see the tree structure. Let's move to the tree structure immediately. Container properties has a leaf name of type string. We had a container interfaces with a list of interfaces. The key in this list is the leaf name. The leaf name is of type string. And in this small example, every interface has a configurable type. And we have the operational state, which is config false. So you see here that every item, if I don't state anything, it's actually defaulted to config true. I could say config true at this point if I'd like. That would be the same. So, as a equipment vendor, you of course need to write your Yangs corresponding to your box. There are numerous of tools. Here I'm just using the Yang mode of Emacs. There are Yang modes for VI. There are Eclipse plugins. You could go search. There are a couple of visual tools as well. For example, there is a NGSoft has a tool where you can Here started on an Acme box with a container, a leaf, and here you can just drag and drop items, and it builds the tool, builds the Yang module as you go. That's also possible. There's also a open source Yang validator, which can also take a Yang and render various outputs. So it's a Google code called Pyang. You can just download and play with that. The same Yang module here, just doing Pyang validates. No errors, it was okay. Pyang has a different set of output modules as well, so you can say, please render a tree output of the same data model. Gives you a handy tree compact structure of the same Yang. Where you see the module name, a container, 2 read writes. Here is a list indicated by the star, and the key is name, and read write type, read write name, and read only to open state. So Pyang is really handy to use. There are the whole idea is, of course, to have standardized Yang data models for devices, and ITF is working on that. So a good source is to go to the NetMod working group, where you can see the ongoing work, standardized Yang data model for interfaces, for IP management, for routing, for SNMP configuration, for system management, etc. So here you can pick up the latest standardized Yang data models. A handy place is also NetConf Central, where you can see a list of data models and different rendering of them. So we can take ITF interfaces, and it renders a HTML output. We can look at the type defs, etc. So this is a very useful place also to check for data models. What does a module look like? If you're a vendor, you need to be capable of writing one. If you are a service provider, you need to be able to receive modules and understand them. So the core parts of a Yang module are the header information, sort of admin information about the specific Yang module. Then you can reference other modules, more about that later. You can define specific types. Then comes the core part, namely the tree structure of configuration and operational data. And Yang also can define admin actions like self-test, reboot, etc. So those are called RPCs. You can also define notifications, which is notifications sent from the device to the management systems. So these are the core parts. Going back to our simple model again, just to keep things down to the earth. There's a module, Acme box, and there's a namespace. So every module has a unique namespace in order to avoid name clashes, and a prefix associated to that. Organization and contact. There should go even more admin information we look into later, like revision statements, etc. Okay, continue. There are two kinds of referencing other modules. You can import another module, and that is the sort of what you expect. That is referencing, for example, a type definition in another module, or referring to another list in another module in order to reference that one. So import are the obvious choice. There are reasons where you might want to split a data model in physical files. So you can have a parent module that includes sub-modules, and those are included. You can view that more or less as a macro expansion where the sub-modules are placed in line within the parent module. So that's for physical separation of files. So that was the module layout. Let's look more into detail in the header information. We did see previously that you put XML namespaces in order to have unique namespaces and avoid name clashes. This should be URIs, and for vendors you typically use an HTTP pattern, so URLs, and define a structure how you put your yangs into that. The prefix. In this case we see a first example of the import statement. So remember, import is where you can reference other stuff from that module. So here I'm importing some standardized yang type definitions. This is an RFC. Whenever I would like to refer to type definitions in IETF yang types, locally here I would prefix them with yang : and a specific type. Here I am including a submodule. So in this case I'm including a submodule called Acme system, which will be sort of macro expansion into the parent module, Acme module. Then along with the module goes some admin information, the organization, contact person, description, and important revision statements. So revisions for every whenever you publish a Yang data model to the external world and add things to it, you should have a revision statement. And this goes into NETCONF capabilities, which we talked about previously. So a NETCONF server publishes its data models along with its revisions, so management system knows which revision of a specific Yang module is being used. Let's elaborate a bit on the submodule. What happened previously? Well, we had a parent module called Acme module. I import, that's plain and simple referencing, but here we did include Acme system. Look up here, here's that specific separate module, which then has a submodule. Note well, submodule Acme system. So submodules can then be included by its parent module, and only by its parent module, so belongs to Acme module. So this is a submodule, can be included by its parent module. Again, it's just to separate the physical definition of the statements into smaller pieces. And the submodule is local. It cannot reference its pieces in its parent module and cannot be included by other parent modules. Okay. Going back to a typical Yang definition, you define the tree structure of containers and lists, and within those you have the actual variables. Those are called leaves in Yang. So here's a leaf called name of data type string. Let's look at what the data types are. So we're walking a little bit bottom up here. Start by looking at what are the available type definitions in Yang. There are a lot of useful base data types, which you see here to the right. So we have the integer of different size, unsigned integers. You have floats, so decimal, that's floats, strings, Unicode strings, enumerated, booleans, bits, binary blob, leafref, very interesting type. We have been using that already in our small example here. We will come back to it later on, but it's so useful, so let's repeat it. Here I have a leaf that I call management interface of type leafref. A leafref is a reference to a specific part in the data model, and here I'm referencing a path that points to a specific interface. So here you see the tree structure ending up with a key into the interfaces table. So that's the purpose of a leafref. We'll look about this in more detail. First, start off by type def. So those were the standard types, but you can do your own types and call them other things by doing refinements of the standard data types. That's a type def. So in this case, I'm doing a type def that I call %. It's of type uint16, but the range is 0 to 100 and a description. So at this point, there is a new type available, and I can define a leaf called completed of type %. And this is of course defined within a module, so within the same module you can just refer to %. If you'd like to reuse this from another module, you would need to import that and put the prefix in front of it. Integers, no surprise here. I'm doing one type def here, type int32 with a non-consecutive range, so 1 to 4, 10 to 20, works perfectly fine. And you can do yet another derivation, picking that as the type, the base type, and you're restricting the range again. So of course the range must be a subrange of the previous one. You can't extend the range again. Here I'm doing a type def of a string where I'm restricting the range. You can also restrict the actual characters. So you use regex expressions so that in this case the NETCONF server will validate that the configured string adheres to this regex pattern. You can have union statements, and the actual value then is one of its member types. So for C programmers, this is no surprise. I have a threshold here, type union, either it's a uint16, 0 to 100, or an enumeration, in this case just with a simple value of disabled. So either it's an integer or it's disabled whenever it's configured. There's also some useful data types defined in RFC 6021. Some of them go back to good old SNMP, where we picked up the SNMP data types, making them available in Yang again. In order to use any of these data types, you'd import IETF Yang types and put a prefix in front of it. Then you can specify a leaf as Yang counter 64, whereas counter 64 is defined in IETF Yang types. So just go and check that RFC for values. That was a quick and brief introduction to the data types. So base data types, you can do your own type definitions, you can do unions, and there are a lot of useful data type definitions in RFCs, for example, IETF Yang types. Now we will move on to another construct, which is called a grouping. And don't confuse groupings with type defs. A grouping is a reusable subtree structure. Imagine you have a tree structure in your device, and on several places you need a small tree with an address leaf and a port leaf. So that's a reusable small tree which you would like to use in several places, and that is called a grouping. So grouping target. It has a leaf address and it has a leaf port. So this is not a type at all. This is a reusable subtree structure. When you define your data tree for the data model, here's a container pair with a container destination. You could of course say leaf address, leaf port, but rather in this case use uses target, where target is a previously defined grouping. So groupings are extremely useful. Put together a subtree definition can be arbitrarily complex, and then you can, along your data tree, just inline that grouping by saying uses target, and now pair destination will have an address field and a port field. Groupings can also be refined. So here again we have the grouping target with an address and the port. Later on in my data model I have a container servers HTTP which uses the target grouping. However, it refines the port definition. The port definition in general can be any port number. It can still be any port number, but the default configured port number in this case is 80. So configuration leaves can have a default value, and that's what I'm doing here. I'm putting a default 80 for the port number. So we've been looking at available types, how you define your own type definitions, and also at the end how you can define reusable subtrees to build your tree. So let's move up, getting more and more to the actual tree definition. The individual values that can be configured or read are called leaves. There are some other as well, but let's start with leaves. So a leaf has a name, curly braces, and some characteristics. There must be a type definition. We've talked about types already, so just be simple here. Let's say the hostname can be any string. You can also put mandatory constraints. So in this case, a configuration without a hostname is not valid. There must be a hostname. So hostname is mandatory true. It also has config true. This is the default, so if I didn't state anything, it would still have been a configurable. So this means that the hostname can be modified by a NetConf client, a management system, and it's part of the get config and backup. That was a config leaf. Another leaf, CPU temp, type int32. You can have units to specify the sort of a display hint more or less what's the units that this variable is measured in. So that's more for display purposes. This is config false, meaning that the NetConf client, the management system, can of course not write to it. Imagine you would like to have a feature where you actually controlled the temperature. Would I have made this into a config true? The recommendation is to follow the useful pattern of a desired value and an actual values, like the if admin status and if oper status. So you would actually better off having a desired CPU temp and another variable called actual CPU temp. So you would write to the desired and you can read the actual value in the other. So then split those kind of variables into two makes it much better to manage. As you've seen, there are a couple of things you can attach to a leaf. What can you attach? Well, we talked about config already. You can specify default values. So if a leaf has a default value, it's by nature optional. You can explicitly state it's mandatory, meaning you can't boot the system without that config being available. Must constraints. We will look at must constraints later on in this tutorial, but must constraints is extremely useful in the context of Yang, going back to requirements from the operators. The NetConf server should validate configurations, and what must constraints is that you can specify Boolean constraints. So for a specific leaf, you can say that this leaf must be larger than another leaf and arbitrarily complex XPath expressions. So that's contained in the data model and not hidden in instrumentation code. The constraints are made explicit in the data model. Type, we've talked about types. When there are certain cases where a leaf might be available or not available. And a when statement is an XPath expression saying this leaf is available if the following expression is true. So that is a formal way of specifying when a specific part of the configuration, for example, is available depending on other parts of the config. Descriptions, just for human readable definitions. We did see units, that's a human readable specification. And status, that's sort of the same purpose as we had in SNMP MIBs, whether a specific definition is valid, meaning current, it's being used and it's okay to use it. Deprecated, meaning be aware, don't use this field, it's gonna be obsolete, whereas obsolete means this definition is gone, no use. Okay, so we've worked from type definitions. Now we've seen how to define actual configurables or read-only operational data with specific types. How do you then put that into trees? And that is containers. So I have a container system, which has a container services, which has a container SSH. And I can put leaves down here in the SSH container. So that's how you build a tree. You build a data model tree by using containers. And these first two containers here, system and services, that's nothing you manipulate from a management system. However, the SSH container is an interesting animal here. There's a container SSH with a presence statement. So these are called presence containers, and presence containers are created by the NetConf client. So in this case, a NetConf client can create the SSH container, and there is semantics attached to that. In this case, creating the SSH container enables the SSH subsystem, and then there are a couple of leaves that you configure the SSH subsystem. Whereas system and services as a management system, you can't manipulate those containers. They have no values. You use them to navigate down to the specific leaves or lists or whatever you're interested in. Okay. Remember, we have seen leaves. So leaves is a single value. It's a scalar or type string or int, which you can read and write depending on config true or not. You can also have leaf lists. So a leaf list is a list of values, every value of the same basic type. So a leaf list, you can manipulate them from the client, from the NetConf client, from the management system. It's a list of values, every value of the same data type. So here I have a leaf list domain search, which contains any number of values, but every value is of type string. Lists in Yang, either they have no semantics and are controlled by the NetConf server, or if there's an explicit semantic attached to the ordering, the NetConf client can manipulate the list and put an item first or after, etc. In this case, the domain search is ordered by a user, meaning a NetConf client can drop an item at a position in the list. So remember, leaf, one value of a specific type, leaf list, several values of a specific type. These are the atoms of any Yang data model. You put those within containers. That's how you build a tree of leaves. That's a very good foundation to start with. And let's go back to our simple example here, just to make things clear. We had one container called properties with one leaf called name of type string. We had another leaf state of type enumeration good or bad. Note well, this is a configurable. This is config true because we didn't say anything, meaning it's config true. A better model would probably be to have, along with that one, a leaf upper state with the actual value of the box. We might configure it to be in good state, but it might not reach that. This would be a config false. It would be a type enumeration. With some enums. So this is a way of modeling these kind of state changes. What you see in here is a little bit of a bad habit, putting the enumeration definitions in line in the data model definition. Doing correct models would be to put some type def on top of the model. You would do a type definition for an admin state, you would do a type definition for operational state, and all the enumerated values on there, and then you rather would say leave state of type admin state and stop there. That would be a more beautiful way of doing it. Okay, so we talked about containers, leaves, and leaf lists. What about lists? A list of users, a list of interfaces. How are lists different from leaf lists? Well, lists can be of any structure. First of all, lists have elements of different types. You can consider them as tables to start with. So You have a column, we have a list of users. Every user has a name, a UID, a full name, and a class. And this is a simple list where you could mirror it with a table. Note well that you don't have just to build flat lists like this, like in SNMP. You can have a list where individual columns in turn are containers of lists, so they can be arbitrarily complex, remember that. But let's start simple. List user, sorry for that. It has a leaf name of type string, and every list needs to have a key. I said every list. Actually, every list that is configuration data need to have a key. You might have list definitions that are config false. For example, if you read some statistics, that list might be a config false. Config false lists need not have a key, but of course, configuration lists need to have a key. In this case, we put the name as a key. You can have one or several leaves as a key. Here comes the different leaves. No surprise. What can you attach to a list? You can specify the maximum number of elements, the minimum number of elements, and in the same way as leaf lists, you can have ordered by. So ordered by system or ordered by users. What about keys then? You reference a specific list element by using the key. And as we define a data model in Yang, remember that's a tree. So referencing a specific item in a list, you'd navigate the tree. Whenever you come into a list, you need to specify the value of that key. And it looks like it's XPath here. So Yang uses XPath for a lot of stuff, for paths, for mask constraints. So imagine this list. We have name, UID, full name, and class, and name is appointed as key in the Yang data model. So if you would like to refer to the name of this user, you would say /user. This would start from the top. This assumes that this user is in the top in the data model. No container, nothing before that one. It's the top container in the Yang data model. The user, square brackets, name equal Yang, /name, surprise, equal Yang. And getting the UID, same thing. Getting the class, same thing. So no surprise here. This is the way you reference individual items. And if the Yang data model would have said that the UID was the key, would look like this instead. You would say UID equal, and you get the other elements. So here you see it's very easy to navigate and understand paths in the data model. If there are some SNMP geeks on the call, you can compare this with understanding SNMP object identifiers and navigating the OID tree in order to get the specific interface. This is straightforward, plain text, just navigating the tree of names. So that's very easy. Keys, that's how you name things, but you might still require non-key leaves to be unique. This example shows where I pointed the UID as the key, which probably makes sense, but still I require the names to be unique. So you cannot configure two users with the same name in this case. If that's good or bad, I leave that to the author, but this shows how you can use unique. So now for leaf refs. I've showed leaf refs a couple of times because they're so important, and let's look at them a little bit more in detail. We had a leaf ref in my model here. Remember, we had a list of interfaces where every interface was named by its name. Later on in the data model, I had the leaf called management IF, which is of type leaf ref, and the path being to a specific interface in the interface list. So this is the specific path. What kind of semantics are attached to this kind of data definition? First of all, a valid leaf ref can never be null or empty. It can of course be optional, which it was in my data model. I can leave this guy empty because I didn't set mandatory true, so it can be just not existing. But I cannot assign it to an interface that does not exist, because it's not a string, it's actually a leaf ref. It's a referential integrity. So must be assigned a value that exists. Also, you cannot delete something that is being referred to. So in this case, if I would have assigned ETH0 as the management interface, if I would try to delete ETH0, that would be rejected and validated by the NETCONF server. There's no way to delete something that is being referred to. So you saw one example, here comes another example. We have interfaces with a name and an address. Then we have the RIP routing, where we have a reference to an IF name. That's a leaf ref referring to interface/name. So this is a path over there. So if 0.19 refers to this specific interface. So far we looked at the pure data definition part of Yang, namely how to build a tree structure, containers and lists of leaves and leaf lists. So that makes up the structure that you can do a get config or edit config to manipulate or read the data. We will now look at another side of Yang, namely Yang RPCs. Yang RPCs are explicit actions that can be performed from the NETCONF client. So it can be self-test, reboot, whatever. So those kind of actions are explicitly modeled as RPCs. Yang data models can also contain notifications which are carried over NETCONF notification streams. So you do explicit definitions of those as well. So we look at how those are defined. An RPC statement. So it's an admin action where you specify the input parameters and the output parameters. The input and output looks like a data definition tree. So all the things you've learned so far on how to build structures of containers, lists, and leaves are valid here as well. But this is a very easy input and output definition. We have an RPC activate software image with an input leaf image of type binary, an output leaf status of type string. But note well, could have been arbitrarily complex structures here. So a NETCONF client would supply a binary leaf here, and then the NETCONF server would respond with a string telling the result of the action. Notifications. So notifications are things that the NETCONF server reports spontaneously. But remember, NETCONF is SSH and requires a session up and running, so NETCONF clients does an explicit subscribe to specific notification streams, and then the notifications are sent over those streams. When a management system subscribes to a stream, it can also request playback, so a NETCONF server can send things that have already been sent before the NETCONF client subscribed. Here we have a notification called config change, where one parameter tells the operator name, and there's a leaf list of changes where every item is an instance identifier. We didn't actually talk about instance identifiers in the Yang section. We talked about leaf refs, and leaf ref need to have a specific path specified into the tree, whereas instance identifiers, these are still references into the tree that can be any, because in this notification we don't know if it's referring to a list of users or a list of interfaces, so therefore we use the type instance identifier, which can be any path into the model. And here we see the actual values for a specific notification. The port of SSH has changed, and these are other changes as well reported over NETCONF notifications. That was RPCs and notifications, very quick. Let's go into a little bit more advanced Yang statements. Must statements. Must statements are extremely important because, going back to requirements, there is a need to validate configurations, a need to keep consistent configurations, and any part in the data model can have must constraints. Let's look at this example before going into details. We have a container timeout, one leaf access timeout, the maximum time. Then we have a retry timer, and for this specific value we specify that it must be less than ... timeout / access timeout. So look here how we navigate the path. We do a Boolean expression for the current instance of retry timer. So the retry timer must always be less than the access timeout. And this is now a Boolean constraint put into the data model. And along with constraints, you can have a tag and an error message for users. And this now is part of the data model. So any northbound client that tries to violate this will fail. And it's clearly stated in the data model rather than hidden in instrumentation code. And the must constraints are specified using XPath10 expressions. So arbitrarily, XPath expressions can be put here with a Boolean output. This was a fairly easy one. You can use XPath language to check all interfaces that are enabled and check the sum. So here, taking the sum of all enabled interfaces divided by weight. So you can build these kind of expressions to check the configuration data. So note well that the must constraints is not sort of limited to the specific path of the model where you are. You can do expressions across the whole model and do calculations across the model. Augment is a very flexible mechanism. Augment is a way for one module to hook itself into another module. So imagine you had the list of users as specified previously, and you would like to augment a new column into the user table. This can be done explicitly in a modular way without changing the already existing, maybe standardized data model. Because you might be a vendor, you pick a standardized interfaces data model, but you would like to add a couple of columns into the IF table. So therefore you can take the standard module, you can write your own specific and augment your stuff into the standardized data model. And here we would like to augment in an expire column into the user table. So you define the leaf expire with its type and the augment statement. So this leaf is augmented into the module with prefix sys system/user. So now this column is available as the fifth column in this user table. And for NETCONF clients, this is transparent. So if you do a get config of the user table, you get all columns. The namespaces will tell where they come from, but you will get everything. And if there is some SNMP geeks on the call here, you remember the augment construct in SNMP doesn't work this way at all. You still need to know where the other part is, and you need to sort of in your mind put them together. Here they put together beautifully, so you can just do a get conf of the subtree and get it. When statement is a way of putting conditional existence of parts of the data model. So in this case, we are augmenting users in the case they are of class wheel. In the case they are of class wheel, they will have a leaf shell. If not, this will not exist. Choice statements. Don't confuse with unions. Unions, that's a part of a data type, and when that specific leaf is instantiated, it picks one of the fields of that union. Choice is something else. It's part of the configuration tree, but there's either you instantiate this specific subtree or that specific subtree. So here, there's a choice of transfer method. So either you configure a transfer interval or you configure a transfer on commit. So choices are exclusive parts of the data tree that are explicitly manipulated by the NETCONF client. Big difference from a union data type. And the previous example was very simple, just one leaf in every choice. But you can have arbitrary structures again. So here we have a choice counters, either case 4 counters or another cases later on. And here, in this case, where we have 4 counters, you will have all of these 4. So there you need to do explicitly named choices like this. Identities. When can you use identities? Well, it's a more flexible way of doing enumerated data types. As we all know, that one of the problems with enumerated are that they're sort of flat and global. You need to have everything in one flat list, and there's no flexible way of extending enumerated. Makes them a little bit hardwired. Identities opens up that problem. Consider identities for as enumerated, but things that can be extended along as we go, and they are hierarchical. So look at this example here. We have an identity called Ethernet, and of course you could do an enumerated data type trying to enumerate every possible Ethernet type. That's pretty hard to maintain. So in this case, rather we do a identity Ethernet, then we do a subtype sort of. Identity ETH1G base Ethernet. So this here is a sub-identity to that identity. 10G, again, another sub-identity to that one. And you can continue. You can define identities that in turn are sub-identities of this one. So you can build arbitrarily trees of identities. So this is a much more flexible way of having extensible, so to speak, enumerations. How do you then refer to identities? And the interesting thing here is, since identities are hierarchies, you can refer to a base type. So here I have a leaf ETH type, which is of type identity ref. So here's an identity. Here I have a leaf that would like to refer to a specific Ethernet type. And when you specify type identity ref, you need to refer to the base. And in this case, I point to the top level. So in this case, I say any identity that is of sub-identity of Ethernet. Here is the Ethernet identity. So all of these definitions would be valid identity refs here. So flexible way of getting away from hardwired flat enumerated. So identities are really useful. Features. When it comes to configuration, a tricky thing is that it depends on how the equipment is really put together. And depending on the type of interface cards and other things you equip the system with, certain parts of the configuration tree might exist. Yang has an explicit way of specifying that with a construct called features. So features are just names. So here's a feature called has local disk. You just define whatever features, give them a name. The interesting thing then is that you can, along the configuration data tree, say if feature has local disk. So the rest of this subtree will only exist when that feature is enabled. How does a NETCONF client discover the features? Well, We need to go back to the hello message again. Remember, 1 hour ago or so, we talked about the hello message where a NetConf server client exchanges its capabilities. So it will exchange its data models, its NetConf versions, its various data stores, and it will also expose its features. So if a NetConf client connects to this NetConf server, the server might say has local disk. That's a feature that is exchanged in the hello message. So that sort of concludes the more advanced parts of Yang. We talked about features, we talked about identities and identity refs, and maybe most important, we talked about must constraints. Those are very important. This actually is the end of this tutorial. So gone through Yang, we go through NetConf. So happy hacking. Thank you. Bye.